All right. Hopefully the rest will join us as we move on. Hi again and welcome. My name is Nelson and I will be guiding us through this workshop today alongside Kevin. And I would like to acknowledge the presence of Megan, without whom none of this would be possible. So if Megan can say hi, we appreciate it. Now, I will move on and share my screen. Hopefully everyone can see this. All right. As we progress, if you have any questions, if you have any points, if you have any concern or just want to say something, please feel free to leave it in the chat and we will be sure to attend to you. Also, be sure to check the chat for any updates from either the members or any of us to see or to get updated on what's going on. Now, the topic of today is natural language processing, or otherwise commonly known as NLP. And we'll be going through this, I want to say, nice and easy, nice and slow, just to get a grasp as to what the whole task is about, what it's for, why we do it, how we do it, and many other things that are very interesting. Now, to begin with, I would like to ask the crowd, what do you think language is? We'll take not more than a minute or two to get some ideas from everyone or anyone. If you want to share, please, you can unmute and just speak. You can leave it in the chat. If you don't, that's also fine. I'm cool with that. No hard feelings. What is language? What do we think is language? What do we perceive as language? Anyone, anything, even an idea would be great. Awesome, Simon. Simon says language is communication. I love it. That's a good one. Else before I shut it off and take some going twice. So, well, I also have a definition of my own from a source, and he said language is a system of conventional spoken by means of which human beings, as members of a social group and participants in its culture, express themselves. This is from Wikipedia, and the key point here is the expression of, could be ideas, emotions by human beings. And as Simon said, that's why okay, Abu Bakr says language is a medium that enables two people to communicate and understand each other. Nice one. Good. So the basic idea that we get from language is that there is exchange. Oh, sorry. Can everyone hear me? I think my internet is a bit shaky. I hope everyone can hear me. Oh boy. Can you hear me now? Okay. Sorry about that. But yeah, as I was saying, at the center of any language is exchange of information. This is how we communicate. We exchange information, whether between, if it's between two individuals or a group of individuals, there's a certain exchange of information. Now, information in many languages, again, please feel free to let me know if you can understand, if you can hear me. If you can't, I'll try to adjust. But yeah, information in any language is carried by its components. The phonemes, which are the pronunciations of the words, the morphemes, this includes the shape and structure of the words. This is how you align the pronunciations to form words. The lexemes, these are combination of words into phrases and sentences. This other will bring these combinations to bring a meaning in whatever sentence or phrase you utter. Context is the intent which we use. Now, to illustrate this, we have. All right. I apologize. Is that okay now? Okay. I am so sorry. All right. Just to illustrate the components of language, we could just change the initial question a bit and change it to what is natural language. And to this point, we've already changed the information that we want to share. The kind of question has changed. We've changed it from language as oh, here, maybe more on this. This is to Simon who asked. Do you want me to elaborate on this slide? Okay, sure. Now, I hope you can hear me. I am so sorry. My internet is acting up. But information in many natural languages is carried by components of the language. These are the phonemes. These are the pronunciations of the words, how you utter them, how you arrange the sounds to make the words. The morphemes, this is the shape and structure of the words. This is how the sounds are put together. And the lexemes are the combination of the words into phrases and sentences. And the syntax are the rules governing these combinations. And the context is the environment in which the language is used. I hope that makes sense. And all right, sorry again. To illustrate that, whoa, sorry. To illustrate that, we could change the initial question by just adding the single word natural. The question was, what is language? But once we say what is natural language, we are communicating a different kind of information. And even the answers could probably change once we do that. And how a person responds depends on these items here, depending on the context or the region or part of the world that they're from, they could answer in the language of origin. And though they are different in these components, the same information of probably the answer is, I don't even know, could be illustrated or could be depicted in 4 or many different kinds of ways. And apart from, whoa, And apart from having spoken or written language, we could also have sign language, which sometimes is expressed as nonverbal cues. And humans have a way of understanding this as opposed to, I want to say, how machines would communicate with each other. Now, what is the difference between natural and artificial language? Well, the first and foremost is that natural language evolves naturally within a community. It is not agreed upon, it is not predetermined, it just comes about and goes on evolving. Whereas artificial language is planned, it is carefully arranged and designed so as to allow communication between human beings and machines. Now, also natural language is culturally dependent, whereas for the most part, you need to be part of a culture to understand stuff like idioms or proverbs or many different things that make up a natural language. Whereas you could just sit in a class and learn any of the artificial languages and be able to communicate with a machine. Some examples of natural languages include the Xhosa from the southern parts of Africa, the German language from Europe, Japanese language from Asia, whereas artificial languages could be C++, Python, or COBOL. Ultimately, both of these kinds of languages are used for communication, whether be it between human beings or between a human being and a machine. I so hope everyone can hear me. Now, here comes the second question of our presentation, and I would love to hear your thoughts on this. Is there a need for computers to understand human language? Since we understand machine language and can send commands to computers or to machines, do we believe that it is necessary for a machine to learn the human language? In other words, is NLP even necessary? Your thoughts are welcome. And if there is a need, why do you think so? We'll take a minute or two to hear everyone's thoughts, then I will proceed.
Hello, Nelson.
Hi, welcome. I
China.
believe this is China. Hi.
Hi. So I wanted to say that I think
Yeah,
natural language processing is necessary because artificial languages are more
yeah,
complex and less friendly. So not everybody can learn it and do it, but
yeah,
at least everyone has their own natural language. If we can have a way that machines can understand the language of each
yeah,
person, that would be easier for them to
exactly.
use the
As a
machines or communicate with the machine.
as a great point of view, great answer. Nice, thank you.
All right.
Anyone else with a thought before I close this up? Yes, Johanna says yes, because computers are getting more and more involved with humans, some of whom have no idea about these artificial languages. This will make it easy for humans to interact with computers. I agree with that completely. And moving forward, I agree with it. I say to a certain extent, it is very useful. And these are some of the benefits I could gather from my sources and experience. And I would say many of these ideas you shared fall into one or more of these categories. Enhancing user experience, where we have things such as the autocorrect in our phones that helps us finish words as we're typing. This reduces the amount of time we need to type, or not only in our phones, now it's even in our email accounts, I believe, or in Gmail mostly. And these just make user experience much better and make apps more easy to use. Also, increasing accessibilities of technologies. This is for stuff like the Google Alexa or the Microsoft Cortana or the uh, Siri app on the iPhone, or I believe many Mac Apple products. This enables not only people, but even people with disabilities to have access to technologies and make use of them in different ways for their benefits. Also, it helps in lowering and ultimately eliminating the language barrier. And this is a point I believe given by both of these ideas from China and Johanna, that since we have so many languages, it would be, and it's also kind of difficult to learn the artificial languages. It will be very helpful if machines could understand human language, then people would just be able to put in commands in their language they're comfortable with, and those commands will be translated to machine language. I hope everyone can hear me. Now, we know that it is important to have machines understand the natural language. Now, how do they do that? They do that through the natural language processing. And for the most part, NLP involves coding information from human language in form that machine interpret go the artificial language in question. For the most part, okay, I'm told that there's a lag. Can everyone hear me? I hope everyone can hear me. Again, I'm very sorry for my internet. All right, I just go back. NLP involves encoding information from human languages into a form that a machine can interpret, or the artificial language. How do you go about doing that? I have this very interesting quote from Galileo. It says, "Mathematics is the language in which God has written the universe." And presuming that that is true, we can encode anything, any phenomenon in a mathematical form. And machines are infamous, if not famous, for dealing with mathematical equations and mathematical stuff. So if we can turn human language into a mathematical form, then that would be very easy for computers or machines to understand the language and apply machine learning algorithms onto these representations for further tasks or tasks ahead. Now, generally, NLP comes in two forms. The first is speech recognition. And in this task, or in these kinds of tasks, the data is in the form of audio recordings, and it involves tasks such as tagging the recordings where you might have multiple speakers in the recordings. And I will take context from work on inspired ideas, is that you will have, you probably, most of the times we probably work with doctors and patients. So you might want to know at what point is the doctor speaking, or at what point is this patient speaking, at what point probably they're taking on pause to take measurements and stuff like that. This is what speech recognition could be used for, or you could use it to classify, given a speaker or anything, anyone in the audio recording, you can be able to classify whether or not this person has certain symptoms of a disease, whether or not, based on the, or not very much symptoms, but you can be able to diagnose, classify what they're suffering from based on the symptoms that they're mentioning in the audio recording. Also, you can use speech recognition, or you can apply speech recognition in transcribing the audio recording, so turning it from an audio into a text kind of data. Also, this is carried out through either machine learning. These are more classic or traditional systems or algorithms, or you can use deep learning algorithms. And in these tasks, information is encoded through a Mel frequency substrate coefficients. These are features you extract from the audio recordings, and you can also further manipulate these features and turn them into an image known as a spectrogram. And this can be fed into deep learning algorithms, as was presented yesterday, I believe, through and you can process the audio in the form of an image rather than any other kind. And this is has been proved to be the state of the art approach or work at the moment. The other form of NLP is text related NLP. And the data in this form comes in the form of text. And it's text that is entered into a computer and not exactly text written on paper. That would change the task first into an image recognition problem, and then you'd have to transform that into an NLP problem. But this form of text is the one you enter in a computer. So probably text from social media, or text in a Word document, in a TXT document, or in a Notepad document, or in an email. Then you can use that text to train your algorithm. Now, this form of NLP involves tasks such as language modeling, where you try to understand the statistical model behind, or the function that makes up the language at hand. And this allows to predict the next word given context of other words in a sentence. This application is widely used in the autocorrect that is in our phones, or in Gmail, or in any other email application. You can also have text classification, where you feed in the text and you try to get a general sense of maybe what is the topic being discussed in the text, or what is its text about. So basically putting it into one or more groups. Also, you can have parts of speech tagging, where you tag the different words, put them in different categories depending on what they represent. Could be a noun, a verb, an adverb, or different parts of speech. This can be done through machine learning algorithms, and these involve, these are the more, again, statistical versions, like the logistic regression, or you can use deep learning algorithms such as the recurrent neural networks that are famous for excelling at this task. Information is encoded through co-occurrence matrices, or the famous embeddings that we will see in a moment. Now, for this presentation, we are going to be delving deeper into the text-related NLP tasks. For more, please feel free to read on speech recognition and tasks of the kind. For any NLP task, context is everything. If we are to consider this example, even to a human, we can see how context is very important. We can read this sentence as "she took a bow and left," or "she took a bow and left." Without the context of the situation, it's very difficult to understand what the word bow in this situation stands for. This is very similar to NLP tasks, where in order to learn or to understand a language, the algorithm basically tries to derive the relationship between words based on their contexts or settings. Now, here comes another question. What do we think an embedding is? And this is the cornerstone of the natural language, text natural language processing at the moment. Feel free. We have 1 or 2 minutes to share our thoughts on what we think an embedding is. If we've never heard of it, it's fine. We're going to go through it. If we have an idea, please, you're welcome to share it. If you want me to power through everything, you can also let me know. I'm cool with that. All right. 2 more minutes if we're thinking of an answer. I will admit they are a bit tricky to understand, so it is fair. But if you have even a rough idea, this is why we're here. All right. I will say that this is a tough one, So I'll take it from here. Now, before we dive into embeddings, let's understand the process of encoding natural language information into more machine-like language. First, the words in the text. Now, for any machine learning algorithm to process any kind of data, the data needs to be in a mathematical form. So most often this is in vectors or matrices. Now, it is important that we convert the text, though they are in bits and the data kind that a computer understands, they're not in the format that a machine learning algorithm can process, because it most often does a lot of math on the data, and the data needs to be in a more mathematical form. And in this case, we convert the text, or rather the words in the text, into vectors, which represent each individual word. And once that's done, the next step is to feed in these vectors into an algorithm. And after that is when the machine learning algorithm applies linear algebra. Basically, these are just manipulations of the vectors to form, or to rather learn a more representative relationship between the vectors, which in turn represent the individual words. And after that, you store these representations, otherwise known as embeddings, for downstream tasks such as modeling the language or analyzing the sentiment in a given sentence, or tasks of the kind. Now, this is the embedding process, and ultimately you get what are known as embeddings. And these specific embeddings where you convert individual words into vectors are known as word embeddings, because you are basically learning the relationship between individual words, and therefore you are embedding the information or the relationship of the individual words and the like. Now, modern representations using neural network-based models provide embeddings that learn that represent the word itself as well as its meaning and use within a given context. And these, once you have embeddings, you can learn, they are in a position to better represent how, maybe say, if you were to say, I'm looking for an example, the quick brown fox jumps over the bench, and you want to say the quick brown cat jumps over the bench, the word embeddings will allow the model to learn that a fox and a cat have very, very close relationships, compared to saying, maybe if you were to predict the quick brown blank jumps over the bench, the model will learn that it is impractical or more or less likely to have the quick brown whale jumps over the bench. So it learns the relationship between different words and their position and their meaning and their functions in a sentence. And this is basically the task of embeddings. And their applications, as stated before, is in language modeling, where you can use both in text-related NLP and speech recognition. And language modeling is basically learning the distribution of words in a sentence and how different words follow each other when you have previous words that started in the sentence. So the example of the quick brown blank jumps over the bench, you will be, the model learning and having a language model allows the algorithm to learn that it is more likely to have a fox or a cat jumping over a bench and less likely to have a whale jumping over that same bench. Now, parts of speech tagging, as illustrated or explained before, is trying to identify the different parts of speech given a sentence. So it learns that this is probably a noun, this is probably a verb, this is probably the end of the sentence, or I want to say the adverb, or stuff like that. And you have named entity recognition. This analyzes the nouns, I want to say, in a sentence and puts them in different categories of, I would say Kevin is in a better position to explain this, but yeah, basically it categorizes the different nouns and puts them in groups. And lastly, and this is probably one we're going to illustrate in a moment, is sentiment analysis, where given a sentence, the algorithm is supposed to understand the underlying emotion, or rather the sentiment. So given a sentence such as, I hate apples, or I really hate riding a bike, the model would have to understand that this is very different from probably saying the same sentence but changing it to, I really love riding a bike, or I really love eating apples. So this is the, in a nutshell, this is what sentiment analysis is. And there are algorithms that are the paradigm, or they're the go-to algorithms for word embeddings. And these again are based on neural networks because they're just so good at it. The most basic of them is the word to vec algorithm, where it tries to encode information between individual words. And moving forward, we have the fast text algorithm. This breaks down the words to their, if we recall, initially I introduced the morphology of a language, which is the basic structure of the language. So the fast text breaks each word into small components and tries to learn the relationship between these components, or otherwise known as subwords, and puts it all together to learn better representations. The flare embeddings and Elmo, I believe, are used to learn more dynamic relationships between words in a language, allowing for, say, in our example, she took a bow and left, or she took a bow and left. The Flair and Elmo would probably learn that given this context, this same word could have different meanings. I hope everyone is with me to this point. If there are questions, I welcome them. If there are concerns, if you want me to go back, is everything okay? Could everyone hear me? All right, thank you, Simon. Thank you. All right, thanks everyone. Please, again, if you have any concern, just feel free to raise it and we'll get to you. Now we're gonna take a case study and try to look at the word to vec at a very, very basic level. We won't be getting into any advanced mathematics, but Kevin will be here to demonstrate on how some of these algorithms work in practice. Now let's consider, again, we are going to consider a Swahili sentence. In the sentence, we want to learn the word, how the word Tanzania fits into this sentence, given the other words in the sentence. What, first of all, part of any machine learning process, you have to pre-process the data. And most common pre-processing in text analysis is lowering or using the lower, turning off the caps on each of the word in the text, just so that once this word is seen in another context, if you have a Tanzania with a smaller t or a lower version of the t, it would not be embedded as two different words. So basically all the text or all the letters in the sentence should be in lowercase. And once that's done, we are basically trying to capture the context of the word Tanzania by observing the surrounding words. And in this version, or in this example, the context window is two, meaning two words to the left and two words to the right of it. What word to vec does is it goes through the entire, and a collection of words is termed as a document. Kevin, feel free to correct me. And a collection of documents is termed as a corpus. Now, what this algorithm does is it goes through the entire corpus as it trains, and the corpus, again, is the collection of documents, which are the collection of the words. it tries to learn it tries to get all the unique words in the corpus and gives each unique word a vector or maps it onto a specific vector. Most often it's a one hot encoded vector. And right here, once you feed in a sentence like this, it will take each word individually. Oh my God, sorry. It will take each word individually and look it up into the mapping that it did and trying to check which vector does this word belong to. And afterwards, it sends that vector through the machine learning algorithm in order to learn the embeddings of the word in question. So right here, it will take the vectors for the word hapa, nchini, Tanzania, watu, wengi. But since the context window is 2 and the word of interest is Tanzania, it will most likely take the first 2 words and the 2 words after Tanzania. Yeah, and once it does that, it tries to learn the relationship between Tanzania and these 2 preceding and following words and tries to map them into an embedding so that the algorithm can learn the proper representation. Now, the benefit of the word2vec is that it provides good representation of words and has, until recently, been useful in doing a handful of tasks, including named entity recognition. And the major setback is its inability to represent words out of the vocabulary it was trained on. So the corpus I spoke of, the collection of documents, ultimately the collection of words, is the limit to which this algorithm can perform. So if the entire corpus contained the words hapa, nchini, Tanzania, watu wengi wanalala, at the end of the day, the algorithm will fail if we say hapa nchini watu wengi wanalala sana, because the word sana does not exist in the corpus. And this is overcome by an algorithm such as fast text. Fast text considers the morphology. As we said before, morphology is the structure and shape of the words. So it breaks down the words into a level such as either the morphemes or the phonemes, and tries to use those to find a better representation of the words. And these broken down items are known as subwords or sometimes known as n-grams. And they have shown to provide better representation and also overcome the issue of the out of vocabulary stuff, because once you have the word Tanzania broken down, and this is an n-gram model where n is 2, so it'll break down into T-A-N-A-N or ta, an, z, za, ni, yeah, right? Then you would be, if any of these, if we consider that in the corpus, most of the words are composed of these items, then any new word will not be very new because it will be able to recognize these items from the existing corpus or the existing representations. And this is just a very small example. In practice, you use a huge corpus with a lot more subwords or a lot more n-grams, and that reduces the problem of out of vocabulary issues. All right, I'm rushing a bit, but I'm basically done. Now, the subword embeddings are very useful and have shown greater performance and are the state of the art or go-to algorithms, but we could push forward and have dynamic embeddings, as said before, using algorithms such as FLAIR and ELMO for better semantic and syntactic representations. You could have subword models capable of learning both the phonemic or syllabic and morphologic structural nature of the context of the text. And you could have concept embeddings. These are different from what we're doing now. They're less in the form of machine learning AI. They're more in knowledge graphs. And you could have stochastic embeddings, and these are more probabilistic in nature, less using vectors, more using distributions. Or you could have hyperbolic embeddings that don't even use vectors in the Euclidean space anymore. They use it in more hyperbolic space where you don't use the cosine and sine to represent relationships, but you use the hyperbolic cosine and hyperbolic sine. Sorry for the math, but you should check these out. They're very interesting. Now, off to Kevin, who is excited and eager to share with us these concepts in action. I hope everyone was okay. If there are questions, please, we welcome them.
Thank you very much, Nelson, for the presentation. As you're transitioning to my demonstration, so I think we're about to go out of time, so I'll just be quick in my demoing. So as Nelson touched before, there are processes that need to occur before when trying to dealing with text. So the first part is even getting the data, where you're going to get the data to train your model for. And there's a website that I like to kind of use. It's called Oscar. So this is a site that's composed of texts that people were able to write scripts for and essentially read through the different websites and try to compose them together in one single file. So scrolling down, you can find they cover a ton of languages, some having more content than others. So you can see like here, English has about 2.3 terabytes of data, whereas sadly Swahili, just a couple of megabytes, 13 megabytes. So for the demonstration, I'll just be using a Swahili corpus so that at least makes sense with the context that you're talking about, Swahili. I will share the script for anyone who wants to like play around with it. That's all right. And again, I'll be keeping an eye on the chat. If there's any question, please feel free to interrupt. I'll be going fast. So yeah. So essentially, this script only downloads the file, and we have the file. So this is how the file looks like, and we need to pre-process it. So as mentioned before, when there's Tanzania capital T and Tanzania small t, according to us, it's the same thing, but according to the computer, those are two separate words. So there are functions here that would try to clean the data by doing things like transforming to lowercase, removing unnecessary punctuation. So there are a couple of dots. There's a bracket. So this script will try to take care of that. So this will be the unclean version, and to the left will be the clean version. So where the brackets were, they're no longer there. Commas are no longer there. Semicolons are no longer there. So that was the pre-processing step. I was told to zoom in. I hope you guys can see now. Right. Let me zoom in again. Okay, so the pre-processing happens at these 3 cells. And for sanity check, to make sure that what's actually happening is happening, we can peek and see that you have, so this is what is referred to as a document, having, which is essentially a list of words, but we call this a document. Yeah, so seems to me like it's done a good job of cleaning the words. Now we go off to represent the word embedding, and with me here I have the 2 formats, the word to vec and the fast text. So as Nelson was kind of introducing you guys to NLP, it takes like a short while to train, but I was training in the background so that we don't have to perform the training here. So I'll just rush through the parameters here real quick. So this size would normally be the number of values to represent the word. So if you'd want to represent the word Jumapili, for instance, so let's say Jumapili. So Jumapili will be represented by 70 numbers. This is what the size is for. The window, be it the context window that Nelson was also talking about. In the example, it was 2. For in the left, it was looking at words like hapa nchini, and to the right, watu wengi. So this one is 5. So it means for a larger sentence, it will look at 5 words to the left and 5 words to the right. These parameters usually have to play around until you know what feels good. And I've decided to stop here because, so given that each word is represented by a vector, it can be handled in a vector way. So to determine if the word Jumapili, what are the other words that are close to it? Usually it's a computation known as cosine similarity, where you can find the distance between two vector points. So with this model, you can clearly see that Jumapili is closer to the words like Jumatatu, Jumamosi, Jumatano. And this is really because in a sentence where you'd say things like tutakutana kesho Jumapili, or tutakutana kesho jioni, or kesho asubuhi. And this is why we can see that Jumapili is closer to such words, right? And the bad thing of this is that, so we trained it as Swahili corpus. So if you use the word like account, okay, so account is there, I guess because this is a news bad. So let's say bicycle. I'll be surprised if it's there. Bicycle. So you can see through an error that bicycle is not in the vocabulary. This is one of the downfalls of word2vec. So to try to deal with that, we have the fast text model, which essentially breaks the word into different n-grams. And here we have the fast text model, already trained on the same Swahili corpus and fed in a word like kesho. But different to how this would handle the word like kesho, you'd see kuna mosi, Jumapili. This one, because of the n-gram nature, would try to break it into other words which would have the same section. So because the word kesho has esh, so it is kesho, onesho, maonesho, yasho. So we really need to know how to play around with these configurations to be able to have a good balance between how it's representing other words with respect to itself and also trying to deal with the out of vocabulary words. And as a bonus, this is something that Team Mary, OB, Nelson, and I worked on within Inspired Ideas. So this is a sentiment analysis task. So we make use of such word embeddings to try to make this machine smart in being able to do a certain task. So the sentiment analysis essentially is a task which involves trying to derive a sentiment or a feeling that one might get from a text. So if you type something like mimi nakuchukia, we can assume that that is a negative, it's a negative comment, so to be negative. Labda mimi nafuraha sana will be positive. So with me here is a sentiment analysis task that can tell if a sentence is neutral, positive, or negative. So just for fun, we can try to demo it. So just randomly type any sentence that you'd like me to try out and see if it works properly or not. Go crazy. I'm gonna read. So if you guys can have any sentence, so I'll go first. Mimi nina furaha sana. So when I do this, oh, sorry. Okay, I'll give it a minute. I think it's loading, okay? Right, so the sentence like mimi nafuraha sana, the model was able to tell us the positive sentiment by 75%, and other feelings it got were neutral by 30% and negative by 12%. And also I realized the math is weird here, it doesn't amount to 100, but there's a special type of math that was applied to getting this result. But yeah, evidently you can see that it was able to give the proper result. If we could try a different sentence, labda mimi nina hasira, to say neutral. Okay, so it will say neutral with 58 and negative with 49. I mean, this is obviously negative, but we can keep on trying different examples. So it's an okay model for sure, but it does deliver results. It's able to tell whether a sentence is negative or positive. Nitakupiga ngumi. So this is also a neutral. So this could be just a normal statement saying takupiga ngumi. Let's try adding nina sira so it says it's a negative with 57%. So essentially this is essentially one of the downstream tasks that you can use by making proper use of embeddings. So sometimes a downstream task would fail because the word, it's not properly represented through the embeddings. Yeah, that is it for the demo. If there are any questions, thoughts, concerns, I think we are out of time. But if there's any questions, please feel free to ask away. And I hope you guys could hear me and I wasn't talking alone the whole time. Thank you, Nelson. All right, if there are no other questions, by the way, some of these standard embedding models are from a package known as Genzim. So you can check that out. It's a free model, has the implementations of word2vec, the typical word2vec, fast text, all of the fun stuff. So you can download the corpus yourself and then test them out yourselves. But if there's nothing else to add, I would like to finish off by saying thank you very much for joining in. These are our contacts, our handles in case you want to reach out and ask anything. Other than that, have a good evening, everyone.
All right. Thank you, everyone. Have a nice evening. Thank you, China. I hope it made sense to everyone. See you.